In this tutorial, we'll explore in more detail some tools and methods of fitting a return distribution. Recall, modeling a distribution assigns a probability to each measurable subset of possible returns. This often involves a mathematical equation known as a probability density function, or PDF. An example of a PDF for the normal distribution is shown here. In the equation, the x variable would represent our financial return data. The mu and sigma variables are parameters that must be estimated. Computing the estimates of these parameters is an example of fitting a distribution. In this specific case, the mu may be estimated by computing the average return, or mean return, and the sigma may be estimated by computing the standard deviation. Recall, the first two moments of a dataset are the mean and variance, respectively. These have a direct known relationship to our estimators. This approach to parameter estimation may be classified as the method of moments. The advantage of this approach is its simplicity and relatively easy calculations, provided the parameter's relationship to each moment is known. One disadvantage is the potential for biased estimates. An alternate to the method of moments is maximum likelihood estimation, or MLE. In words, MLE seeks parameter values that make the observed financial return data most probable, or likely. For example, given the distribution shown here, let's walk through a few parameter estimates to illustrate the point more clearly. In this example, we'll attempt to fit parameters for a normal distribution model, mu and sigma. Our initial guess, let's say, is that mu equals 1% and sigma equals 5%. Visually, if we overlay our mathematical function over top the distribution, we get the following. From our graph, the red line appears much wider than the actual data. This implies that it is not likely or probable that our actual data came from the distribution modeled by the red line. The maximum likelihood estimation process would then attempt to select new parameters. Let's say it selects mu equals 1% and sigma equals 3%. Visually, we can see that the width is more appropriate, but the center of the distribution appears misaligned. The MLE process will search through several iterations and find the set of parameters that make the observed data most likely. What defines most likely is a mathematical function called a likelihood function, which relates to the probability density function. Technically, each observed data point has an associated probability of occurring defined by our candidate PDF, the red line. Each observed data point's probability is computed and multiplied together with every other data point's probability. This yields an overall likelihood measurement. In sections where there are more actual observations, if the red line is relatively low, indicating the red line views these as unlikely events, then our likelihood measurement will be relatively low. Generally speaking, parameters that yield a red line that most closely matches the data, the higher or better the likelihood measured by the function. Our final distribution model looks like this. There will still be places where the distribution and red line appear to deviate. How do we know if we've selected the best model? MLE only provides optimized parameters, but it does not say anything about the type of distribution model. In this case, we assumed a normal distribution. But is that the best model to choose? One visual check is a tool called a QQ plot. QQ stands for quantile to quantile plot, which essentially plots observed quantiles against theoretical quantiles predicted by the model. The main point here is that if the model selected is appropriate, we should see a relatively straight line. In this case, both the left and right tails deviate substantially from a straight line. This implies that a different model accounting for either fat tails and/or skewness should be attempted. We'll attempt to fit a skewed t-distribution, which has 4 parameters to estimate. Using the same MLE process, we estimate these parameters and see the resulting density function. Visually, the histograms appear to reveal a closer match, but let's check the QQ plot to be sure. Compared to the normal distribution model, we do see a much more linear relationship. This implies our skew t distribution is a better selection. Other, more quantitative tools may also be considered to verify the quality of fit. The overall likelihood value is higher in the case of the skewed t-distribution, confirming our conclusion. Sometimes, however, simpler is better. While the skewed t-distribution fits better, it is a more complex model using 4 parameters instead of 2. Other metrics, such as the Aki-Iki Information Criteria, or AIC, will account for more complex models. For AIC, lower numbers are better, and while the skewed t-distribution is more complex, the extra complexity is worth it for this example. This completes the fitting distributions tutorial.